Let's consider two massive bodies, one describing a circular orbit around the other. The force responsible for the motion is the gravitational force, which is a conservative force, and consequently, the energy of the system remains constant over time. These bodies could be, for example, the Earth and the Sun. Now imagine an inertial observer on a spacecraft moving parallel to the plane containing the circular orbit. From the spacecraft, what trajectories would be observed for the Earth and the Sun? Is the system's energy seen from the spacecraft still constant? It should be, right? Before we begin, it is worth highlighting three aspects. Number 1. A prior knowledge of the very basic concepts of classical mechanics is assumed. Number 2. In the video, two inertial observers are considered, but within the framework of Newtonian mechanics. Relativistic mechanics is disregarded. And number 3. The orbit of celestial bodies is generally elliptical, but for simplicity we consider a perfect circular orbit, which is fully consistent with the laws of classical mechanics. We begin by reviewing the basic notions of uniform circular motion. For this, we consider a wheel that rotates but does not translate, and a point on its rim. We establish a first reference frame, which we call S sub 0. Likewise, all physical quantities observed from this frame will carry the subscript 0. We place frame S sub 0 so that the lowest point of the wheel coincides with the origin of coordinates, and the center of the wheel lies at position 0, r, with r being the radius of the wheel. The position of the point on the wheel is completely specified by the parameter theta, which is the angle formed with respect to the vertical axis of the wheel. Using elementary trigonometry, it is easy to see that the x component is minus r times sine of theta. On the other hand, to determine the vertical component shown in magenta, we take into account that the green segment is r times cosine of theta. Subtracting this term from the yellow segment, which is the radius of the wheel, gives the length of the magenta segment, r times 1 minus cosine of theta. Once the position vector in system S sub 0 is determined, the velocity vector is obtained by differentiating with respect to time. We take into account the chain rule in that the derivative of theta with respect to time is the angular velocity omega, which is constant given that it is a uniform circular motion. Differentiating, we immediately obtain the following expression for the velocity vector, whose module is constant and equal to r times omega. Now consider a second reference frame, which we call S. The physical quantities perceived from this reference frame will not be followed by any subscript. This frame, seen from S sub 0, translates to the left, but not with just any velocity, with the same speed as that of the wheel's rotation. Next, we analyze the motion of the point on the wheel as observed from frame S. Now, the wheel not only rotates but also translates to the right with velocity capital V. Therefore, the point in blue has two velocity components. On the one hand, there is a rotational velocity v sub 0, whose expression we obtained earlier in the frame S sub 0. On the other hand, there is a translational velocity capital V. The velocity of the point v, observed in frame S, is the sum of these two velocities. In physics, this operation is known as a Galilean transformation. Performing the vector sum yields the following expression for velocity v. Notice that while the speed observed in S sub 0 is constant and equal to r times omega, in frame S, the speed of the point varies due to its dependence on theta. Let us look at some particular cases for the angle theta. When theta equals 0, the point's velocity is 0 because the rotational and translational velocities, equal in magnitude, point in opposite directions. The lowest point of the wheel is said to be instantaneously at rest. For theta equal pi over 2, the velocity becomes r times omega in both its horizontal and vertical components. For theta equal to pi, the rotational velocity and translational velocity point in the same direction, so the point's velocity is maximum and equal to 2r times omega. Since we know the velocity vector in frame S, we can determine the position vector by integrating. We set the position at time t equals 0 to be the origin. This means that at the initial instant, reference frames S and S sub 0 coincide. Taking into account that theta equals omega times t and carrying out the integration, you can verify yourself that the following expression for the position vector in frame S is obtained. This is the parametric equation of the cycloid. Specifically, the cycloid is the curve traced by a point on the rim of a wheel that translates without slipping. It is worth highlighting the procedure by which we deduce the cycloid equation. We started from the velocity vector in frame S sub 0, where the wheel only rotates. Then, we obtain the velocity vector v in frame S, where the wheel both rotates and translates without slipping, through a Galilean transformation. Finally, we obtain the position vector providing the parametric equation of the cycloid by integrating the velocity vector. This is a much more efficient way of deducing the equation of the cycloid than the purely geometric classical method. Now that we have reviewed the fundamental concepts of circular motion, let us return to our Earth-Sun system. In reference frame S sub 0, the Earth orbits circularly around the Sun. The energy of the system, E sub 0, is equal to the sum of the potential energy, U sub 0, and the kinetic energy, K sub 0. In a basic mechanics course, one learns that the gravitational potential energy equals the following quotient, where G is the universal gravitational constant, big M is the mass of the Sun, small m is the mass of the Earth, and r is the orbital radius. On the other hand, in the expression for the kinetic energy, we have the Earth's orbital velocity v sub 0, which we can easily derive from Newton's second law. From now on, I will go faster through the calculations, but I encourage you to pause the video and derive them yourself. Once we have the orbital velocity, we substitute it into the expression for the energy. Finally, we obtain that the energy in frame S sub 0 is equal to minus g times big M times small m all over 2r, which is a constant quantity. But all this is quite simple and does not add anything new. So let us complicate things by reintroducing reference frame S. This is the spacecraft's frame, which moves to the left with a speed equal to the orbital speed, namely the square root of g times m over r. In frame S, the Earth is observed to describe a cycloid, while the Sun, which was at rest in frame S sub 0, moves in a straight line to the right. The Earth corresponds to what earlier was a blue point on the wheel, while the Sun corresponds to what earlier was the center of the wheel. The energy in frame S is also the sum of potential and kinetic energies. The potential energy has the same expression as in S sub 0, since the distance between objects does not change when switching between inertial reference frames. That is, the separation between Earth and Sun remains constant during the motion and equals r, just as in frame S sub 0. However, the kinetic energy is indeed different, since both Earth and Sun now move. Since the Earth describes a cycloid, we know the expression for its speed, where now r times omega, is the square root of g times m over r. We substitute v into the energy expression. On the other hand, we have the speed of the Sun, u, which is constant at all times and equal to the square root of g times m over r. We substitute this result as well, finally obtaining a long expression, in which a dependence on theta appears, and therefore the expression is not constant in time. What does this mean? Does energy fail to remain constant in frame S? How is this possible? Houston, we have a problem. Let us recap. The kinetic energy in frame S takes the following form, the same as in frame S sub 0. The difference is that in S sub 0, the speed is constant and equal to r times omega, so the kinetic energy is also constant. On the other hand, in S, the speed is not constant, and consequently, neither is the kinetic energy. This is due to the dependence on theta. Classical mechanics states that if all the forces involved in a system are conservative, as gravitational force is, then the system's energy remains constant. In S sub 0, this holds true, as the energy equals minus g times big M times small m all over 2r. However, in frame S, we obtained an expression for the energy that is not constant in time because of the presence of cosine of theta, given that theta equals omega times t. We are therefore faced with an apparent paradox that must be solved. Again, I encourage you to pause the video and try to solve it yourself. So far, we have considered the Earth to perform a circular orbit around the Sun, with the latter remaining at rest in frame S sub 0. The centripetal force responsible for the motion is the gravitational force. Newton's third law states that this same force, but in the opposite direction, also acts on the Sun. What happens is that since the Sun is much more massive than the Earth, it is usually assumed to remain at rest while only the Earth moves. However, this is merely an approximation. In a binary system, like the Earth-Sun system we are considering here, both bodies perform a circular motion. That is, both Earth and Sun describe circular orbits around the center of mass of the system. Let small r be the orbital radius of the Sun and big R the orbital radius of the Earth. Taking this subtlety into account, we update the expression for the energy in frame S sub 0. Now, the kinetic energy has contributions from both Earth and Sun. Proceeding in the same way as before, from Newton's second law, we obtain that the orbital speed of the Earth is as follows. Note that in the limit small r equals 0, the expression we previously obtained is recovered. We substitute the result for v sub 0 into the energy expression. Similarly, we obtain the orbital speed of the Sun, which vanishes in the limit small r equals 0. Finally, we obtain an expression for E sub 0 which is also constant, as it must be. Let us move on to frame S. Earlier, when we assumed the Sun was at rest in S sub 0, we found it to move in a straight line in frame S. But now that we have discussed that in S sub 0 the Sun also describes a circular orbit, in S it describes a curved trajectory, which in mathematical language is called a courted cycloid. In the previous simulation, we exaggerated the orbital radius of the Sun for the sake of comprehension. A more realistic simulation would be the following, where the yellow curve traced by the Sun more closely resembles a straight line. The fact that the Sun does not move in a straight line gives a clue that its speed is not really constant, and the kinetic energy losses of the Sun are converted into kinetic energy gains of the Earth and vice versa. In this way, the system's energy would also remain constant in S, thus resolving the paradox. Let's verify this explicitly. To do so, we return to the frame S sub 0 and determine the position vectors of Earth and Sun. We then differentiate the latter to obtain its velocity vector in S sub 0, as we will need it later. We know that the energy E sub 0 in frame S sub 0 is constant. We want to check that in frame S it is also constant in order to solve the paradox. Since the potential energy is constant in both frames, the only term that could make the energy variable is the kinetic energy. To determine the kinetic energy, we need to know the speed of the Earth, v, and the speed of the Sun, u. These can be obtained from their respective velocities in frame s sub 0 through a Galilean transformation. In s sub 0, we saw that the Earth's orbital velocity was this, so the velocity in s, taking into account that the relative velocity between frames is r times omega in the x direction, takes the following expression. Equivalently, from the Sun's velocity in s sub 0, we obtain the corresponding velocity vector in frame s. We are now ready to calculate the kinetic energy. We substitute the result for the Earth's velocity vector. And we do the same with the Sun's velocity vector. Then we expand the square and simplify, bearing in mind the Pythagorean trigonometric identity, leaving the left-hand summand as follows. We do the same with the right-hand summand. We group the terms multiplying cosine of theta, as this is the term that makes the energy expression a variable. For the system's energy to remain constant, the coefficient of cosine of theta must cancel. That is, if big M times small r minus small m times big R equals 0, then the kinetic energy is constant and therefore, so is the total energy. To demonstrate that the coefficient indeed cancels, we use the fact that the forces are the same in any reference frame. For simplicity, we go to the frame s sub 0, where the bodies describe circular orbits and the forces are centripetal. We apply Newton's second law, keeping in mind that the acceleration is purely normal, both for the Earth and the Sun. Finally, by equating both equations, we obtain the equality we were looking for. In this way, it is proof that the energy in S is also constant, thus solving the paradox.
Toma!